All right, let's go ahead and begin. This is variable speed heat pumps, and we're going to focus on the Midwest, the Chicagoland area here. All right, so the first thing is you probably noticed there are two new heat pumps that have been released recently from Bryant and Carrier. The Carrier one was released early last fall, around August or September, and the Bryant one was released this March. They're very similar machines. The Bryant unit is a 280 ANV model, the V standing for variable speed, and the Carrier is a 25 VNA. These guys come 2 through 5 tons in full sizes only, 2, 3, 4, and 5 ton. There's no half sizes because obviously with a variable speed product, the variable speed compressor can ramp down a little bit to accommodate for that. So we don't have any half sizes. Additionally, we don't stock 2-ton sizes. We only stock the 3, 4, and 5. We can get to 2 tons if you needed it, but so far the demand has been very minimal for that small of a unit. These heat pumps do need to be paired up with a Evolution or Infinity communicating indoor unit. So that could be a fan coil or it could be a furnace, but it has to be a unit that has that type of controls in it because we're going to be coordinating a lot of variable speed things at one time here to kind of make it all work. There's going to be variable speed compressors, variable speed condenser fans, electronic expansion valves, indoor blowers, and all those things have to be coordinated together to make sure we're getting this thing to operate correctly at the right airflow speeds and so forth. So you do have to have an Infinity or Evolution furnace or fan coil, and you have to have an Infinity or Evolution controller on the wall in lieu of a standard thermostat. Specifically for the Bryant side, it needs to be the -D part number, which would be the most current version. So at the end of the part number, they append a -D as in David. For the Carrier one, it's -V as in Victor. Those are the two most current ones, and those are the two that you would need in order to work with this product. So let's take a quick step back and look at regular heat pumps just for a second so you can kind of understand what they do. Hopefully most of you guys on the call probably know what a heat pump is, but just to be clear and to make it easier for you to explain to homeowners. So on the left side here is kind of the way we explain it to homeowners, and the right side is kind of the way we explain it to you guys. But basically the first thing to getting a homeowner to understand what a heat pump is going to do for them is to get them to really understand what an air conditioner does for them. They all think that air conditioners make their air cold, which obviously it does. It's not really adding coldness to the air, if you will. It's really extracting heat, right? So as air goes across someone's evaporator coil, hopefully you guys can see my mouse on here. I'm not sure if you can or can't. Hopefully you can see my mouse. As air goes through the evaporator coil inside your furnace, we're basically extracting heat out of the air of your house and sending it outside and rejecting that heat out your condensing unit. So we suck heat from the inside, reject it to the outside. A heat pump does the exact same thing. It's just an air conditioner running in reverse. So we suck heat from the outdoor air, push it through the refrigerant lines into your indoor unit, and dump the heat there. So we're pumping heat from outside to inside, hence the reason we call it a heat pump. So a heat pump is nothing more than an air conditioner running backwards. We basically swap the responsibility of the evaporator and condensing coils. The condensing coil is now inside, the evaporator coil is now outside. If you look at it from a piping standpoint over here on the right, there's mainly one component that's really different from a service standpoint, and that's the reversing valve. That's this guy up here with the 3 ports on top and 1 on the bottom. His job is basically to just switch the direction of the refrigerant flow in order to swap the condenser and evaporator. Oftentimes you'll hear heat pump guys refer to them as indoor coils and outdoor coils instead of condenser and evaporator like we normally do on the air conditioning side, and that's because each coil does both jobs depending on the season. In terms of these new units that we have and how they're different than regular heat pumps, because heat pumps have been around for whatever, 40, 50 years, something like that. The main big difference here is that these guys are variable speed. They have inverter compressor technology. Now, inverter compressor technology is not new to the industry. We've been doing that on duct-free splits for several years now. What's new is having that kind of technology in a standard residential style heat pump condensing unit that we can put on with a regular, style ducted furnace. So the duct-free split guys have been doing it for a while. This is really the first time you're seeing it on a ducted system. There's one other manufacturer that has a unit, but it's an oddball manufacturer, so we don't really need to address that one. The efficiency of this thing is phenomenal, though. It's 13 HSPF, and we'll talk more about what HSPF means, heating seasonal performance factor. But 13 is the best in the industry. It is very efficient. At the 3-ton size, which is the most common size we've been looking at lately, it's 29% more efficient than the nearest 2-stage heat pump competitor. And it's 68% more efficient than the legal minimum that a heat pump can be. So this is a really efficient piece of equipment. We also do what we call dual fuel systems or hybrid heat systems, where we combine heat pumps with other fuel sources, typically a gas furnace, sometimes an electric furnace, sometimes even hydronics, in order to have these guys have the most efficient operating times of the year when they can, and switch to other source at other times of the year. We'll talk more about that. And then on the cooling side, which is the season we're obviously entering right now, and our previous weekend here has made that more obvious, this is going to be the best dehumidifying air conditioner, if you will, that you probably have ever had in you or your customer's building or home. This guy can do about 60% more dehumidification than a standard unit would be able to do. And a lot of that has to do with some of the new airflow capacities we'll be able to use with this guy. We'll talk about that today. So real quick, hybrid heat systems. This is not a new thing at all. Many manufacturers have called it dual fuel for years. The Carrier and Bryant folks have been calling it hybrid heat for, I don't even know, 8, 9, 10 years. And the reason that they do that is to basically get a play on the hybrid car phenomena, or trend, if you will. Tons of people have hybrid cars now. Start with the Priuses 10 years ago, but now everybody's doing it. And the whole idea is to piggyback off that marketing power that they use by using that hybrid type name. If you tell someone you got a hybrid car, they pretty much understand you have an electric motor and you have a gas motor in that car. If you tell someone you have a hybrid heating system, they might be able to conclude quickly in their head that you have 2 types of heating. In this case, both gas and electric. This kind of shows how that works a little bit. This is a chart from left to right is outdoor air temperature. And we'll show you some charts in a little bit that actually have scale to them. This just gives you an idea for your homeowner. So when it's really mild outside, we'll use the electric-based heat pump, like it shows over here on the right. When it's really cold outside, we'll use the gas-based furnace system. And then in the middle, we'll use a combination of the two, or we'll switch back and forth depending on the kind of system that we have. And those temperatures change based on what your fuel prices are. So we'll plot those out in a minute. The big advantage of having one of these hybrid systems is the ability to buffer any fuel increases that happen with your utility provider, so you don't feel as much pain as your neighbor, basically. So if gas prices were to increase 28%, which is very possible because in the past 4 or 5 years, gas prices have decreased like 40%, so it's quite possible they could go up again in the next year or two. But if gas prices went up 28%, most people with a furnace system would pay 28% more on their gas bill. However, if you have a hybrid system where you have a heat pump and a furnace combined, if gas prices go up 28% and electric prices stay the same, you're probably going to see only about a 4% increase in your total heating costs. Because we'll switch more hours onto the heat pump and less onto the furnace. That's kind of the nice thing about that hybrid type system. So some of the reasons why we haven't done a huge amount of heat pumps here in the Chicagoland area over the years, and this is based on a survey that we did back last summer asking folks why they don't do a lot of heat pump work. The big answer that came back was the cold blow. Consumers don't like having cooler air blow on them. I can heat anybody's house with 85, 90 degree air all day long, all year long, no matter the temperature outside. But if I'm heating your house with 85 degree air and 85 degree air is blowing across your 92 degree skin surface temperature, it feels cold to you and you're not going to like it. So we really need to keep the air temperatures up above 100 degrees for comfort. Over the years, heat pumps have not been able to do that. We solved that problem in recent years, and we'll talk about that. I also get a lot of people saying that you can't put a heat pump in cold climates. So we'll specifically talk about the various run hours we can get in the Chicagoland area, as well as even colder climates. And then just for point of reference, of the top 5 heat pump selling states in the country, 2 of them, Wisconsin and Minnesota, are much colder climates than we have here in Illinois. So if people in Wisconsin and Minnesota can use heat pump technology to save money, I'm pretty sure we can do it here in Illinois as well. Had some people say that these units were harder to service than a regular air conditioner. And after prying into that one, it seems to come down to 2 things that both relate to the reversing valve. One is the reversing valve itself. Guy says one more component they have to think about and troubleshoot. And 2 is wiring the reversing valve to your thermostat. That one is kind of a challenge. It involves some extra wires. Some heat pump manufacturers label the terminals O, some label them B, which means normally open and normally closed. The thermostat guys do their thing as well with O's and B's. and you got to really kind of pay attention to both pieces of equipment, the stat and the heat pump, in order to wire them together to correctly. It is kind of a pain in the ass. The nice thing about the Infinity and Evolution is that there is no thermostat involved. We're using the Infinity and Evolution controller. It's 4 wires no matter what, A, B, C, D, and there's nothing else to think about whether you have a heat pump or an air conditioner. It wires identically. Everything's done over communication. So that's been easily resolved. Reliability issue. After prying into that one, most folks said they were concerned about longevity of a heat pump because you're running it so many more hours. There's numerous studies out there that show that heat pumps last just as long as air conditioners do, and in some cases even longer, and maybe that's because they're typically better maintained. But there has been proven to be no reliability issues with a heat pump as related to an air conditioner. Expensive to install. For the most part, a heat pump, labor-wise, costs the same thing as a regular air conditioner would cost to install, with the exception of wiring up that reversing valve to the thermostat. But once again, we've eliminated that, so that should be pretty equal. So really only the price difference is a heat pump versus an air conditioner, which is a few $100s more. And then the payback scenario, that one can be legitimate depending on your current heating fuel source. Natural gas customers may have a challenge in our area paying back a heat pump quickly, whereas propane, oil, and electric customers will pay it back nearly instantly. We'll talk about all these things in more detail here. So the first one, the cold blow scenario, there's a couple different things we've done to kind of resolve that. The first one is when we start these systems up, we don't immediately blast full airflow when we turn on a call for heating on the heat pump. What we do is we initially turn on the compressor and the heat pump and let refrigerant flow to start warming up that indoor coil, which is the condenser coil. It used to be the evaporator coil, right? So we let that guy start warming up for like a minute or so. Then we start ramping up the indoor blower speed in order to get up to full airflow. It's kind of similar to what we do on gas furnaces now. We fire the burner, and then after things get warmed up, then we go ahead and turn on the airflow so you don't get that burst of cold air. So that's one thing that we do to help resolve that. The other thing that we do is try to maintain a higher operating discharge temperature for as long as possible. So you see 2 lines on the graph here. The blue line is what would happen on a standard heat pump. So on this scale here, you see we're starting at a mild 60-degree day. As it gets colder and colder outside, the discharge air temperature over on the left-hand side of the graph continues to drop 100, 95, 90, 85. By the time we get down to like 5 degrees, we're talking about 80-degree discharge air temperature, which may be able to heat your house, but it certainly doesn't feel very good. Whereas this red line represents what we do on the variable speed heat pumps, which is we target like 104 degrees, say. We try to maintain that for as long as possible. So as the temperature drops outside, we continue to keep the discharge air temperature high. And the way we do that is by slowing down the indoor fan blower. So we continue to ramp up the outdoor condensing unit's capacity as we slow down the indoor blower speed. If we move air across the indoor coil slower, it'll have more time to pick up the heat that we're pushing into it, and hence a higher discharge air temperature. Now, with that being said, we can only do that to a certain point. In this example on this chart, when we get down to like 6, 7 degrees outside, we've slowed down the blower as much as we can. We've ramped up the condensing unit as much as we can. The only way to get more BTUs at that point is to start speeding up the indoor blower, at which case you see the discharge air temperature start dropping. However, by the time we get below 10 degrees outside, we are probably already switched over to our gas furnace or electric supplementary heat anyway, so it's pretty much a negligible point. Let me take a quick look over here. I saw some questions come in. Let me see if any of them are ones we can try to address here. One question here is, can you use a zone package, which I'm assuming is referring to a zone damper system? The answer is absolutely yes, and we'll talk about that a little bit more at the end of the hour here. I got some slides on that specifically on how it works with the zoning system and how it's more advantageous to use this kind of heat pump versus a regular heat pump or air conditioner. If anyone else has any questions, please do type them in the chat box down on the right-hand side, and I'll address them. All right? So next slide here. So addressing the cold climate scenario, here you'll see the third line down is Chicago, Illinois, representing how many operating hours we have here. This chart is what we call for bin hours. Bin hours are basically every hour of the year. So there's something like 8,760 hours in the year. And if you look at Chicago, of those 8,700 hours, 6,000 of them are below 65 degrees outdoor temperature. So the vast majority of our year, it's below 65 degrees outside, which doesn't feel like it right now, but obviously the rest of the year it's pretty cool. We often think of Chicago winters as being, cold 0-degree weather, which we usually get, although this winter we didn't get that. But the reality is we don't hardly ever get that. Yeah, there's always the 0 or -5 or -10 degree days that we get, but they're very few hours of the entire year. So the second column here, where it says above 30 hours, that's how many hours are between 30 and 65 degrees outside. So what are our heating hours throughout the year that are above 30 degrees? It's 4,500 hours. More than half of the entire year and 3/4 of the heating year, we have temperatures above 30 degrees, which are a prime opportunity for heat pumps, even regular heat pumps. If you look at hours above 20 degrees, which is really kind of the range we're going to get into with these extreme and green speed heat pumps, 5,400 hours are above 20 degrees, so between 20 and 65 degrees outside, which means 90% of our heating hours are above 20 degrees outside. So if I got a heat pump that can handle lower temperatures like one of these green speed or extreme heat pumps from Bryant and Carrier, I can handle pretty much 9/10 of my year that way, and only 10% of the hours do I have to run my furnace. And then to give you some more extreme examples, if you just look at this chart, some of the colder places that we ever think about, in the Midwest here, like up in Minnesota or International Falls, right? That's the place on the map, on the weather map that they always show you as the coldest place, right? It's always got the -20 degrees. Even then, look how many hours they have, 4,500 run hours above 30 degrees, 5,500 hours above 20 degrees. Yeah, they get a bunch of -20 degree days, but it's not very many hours of operation. So we have plenty of time that we can run heat pumps in our climate for cold weather. And then just to show you graphically here, all these bars in red represent the number of heating hours that we have for 5-degree temperature bins. So if I pick one of these lines here, like this one right here, 32 degrees, right? If I look up that 5-degree band right around 32 degrees, so from 30 to whatever, 30 to 35 we'll say, it's like 650 hours, right? The 37-degree band's another 600 hours. So you can look and see the bulk of the hours are between 20 and 60 degrees, the most red bars here. You can also see the bulk of the operating hours are in the heating mode and not the cooling mode. So it makes you wonder why we're talking about, this heat pump, right, going into the cooling season here. And the reason we're talking about this heat pump on the webinar today is really not for heating. The heating season is going to give us the energy savings to make this thing worthwhile. The cooling season has huge comfort benefits, which we're going to talk about in about 10 minutes or so on the dehumidification side of the equation. So when we're picking one of these heat pumps, we got to figure out at design time when the heat pump's going to have to shut off and when we're going to have to turn on another heating source, right? So we look at what's called a balance point. There's two types of balance points. There's a thermal balance point, which is what outdoor air temperature can my heat pump no longer make enough BTUs to heat my house. And then there's the economic balance point, which is based on how cheap gas is or how expensive it is versus electric. At what economic point should I go ahead and shut this off and turn on my gas furnace, right? So we need to find both those numbers, and one of those two numbers is going to dictate when we decide to change the heat pump over to gas furnace operation. Normally what we've done on heat pumps over the years is we size the heat pump for the cooling mode, right? And this is a pretty normal thing that we have to do. If we were to size the heat pump for the heating mode, we'd have like twice as big of a heat pump as we might want for cooling season, and it'd be a problem, right? So if I said, oh, your cooling load's 3 tons and your heating load is 6 tons worth of capacity, right? So 6 tons would be 72,000 BTUs, which is a pretty normal size house, right? Well, I can give you a 6-ton heat pump, but come summertime, it's going to be twice as big as it should be, and it's going to be really bad at dehumidifying your house. It's going to cycle on and off and beat itself to death. So traditionally, we've sized heat pumps for the cooling load, right? So if you came up with, let's say 33,000 BTU cooling load, right? I'd either have to give you a 2.5 or a 3-ton heat pump. Hopefully, I would give you a 2.5 so I wouldn't be oversized. However, with these variable speed heat pumps, because they're variable speed and we can ramp them down to avoid having too much capacity, instead of telling you to size the heat pump for the cooling mode or even round down, we're going to tell you to round up to the next larger size. So if you had a 33,000 BTU cooling load, we'd say at least put a 3-ton heat pump in, maybe even the 4-ton heat pump. And we'll look at that here in a minute. So we're going to try to size this more for the heating load and less for the cooling load. Now we can't size it for the full heating load in our climate just because the heating BTUs are so much greater than our cooling BTU needs. But we're going to try to size it closer to the heating load as we can to avoid running the furnace as much as possible. So this here shows you the way we used to do these thermal balance points, and I'll show you the way we do them now in a minute on software. But the way we do them is we take one of these charts out of the book, and this is not even a variable speed unit on here. This is a regular two-stage unit that's on here right now. We take this chart from the book, which on the bottom goes from -10 to 80 degrees outside, and then on the left it goes from 0 to 80,000 BTUs. We plot this red line on the chart, which represents the load of somebody's house. And normally we do a load calc at the design point, which in this case, let's say it's -10 degrees, and this guy needs 60,000 BTUs on a -10 degree day. Great, we plot that point. Then we got to plot one other point on this chart. So you could, do another load calc, but set it for 10 degrees outside or something and get this 45 degree point. And once I got 2 points, I could draw a straight line through them and see what would happen at pretty much any outdoor air temperature. So in this case, at 65 degrees outside, this guy doesn't even need any heat for his house at all. He basically needs 0 BTUs at that point. So by looking at that, I can plot that on the same chart here that has the heat pump capacities that are published by the manufacturer. There's 5 or 4 of them listed here, a 2, a 3, a 4, and a 5 ton, and then the half size would just be halfway in between basically. So if I put a 2 ton heat pump in this guy's house, if I followed that line down, when I got to, we'll call it 43 degrees outside, I would no longer be able to make enough heat with the heat pump in order to heat this person's house. If I put the 3 ton in, which is where the red dot is, if I follow that line at 36 degrees outside, that I wouldn't be able to make any more capacity. I wouldn't be able to make enough capacity below 36 degrees. If I put the 4 ton, then my cutoff point would have been whatever, 28 degrees. If I put the 5 ton in, I would have gotten down to 24 degrees outside. Now, how do I pick between the 2, 3, 4, and 5 ton? Well, I need to kind of know the cooling load because I don't want to be grossly oversized here. And then I also got to think about how much ductwork airflow I can handle. So here shows you an example very much like that, but with the variable speed heat pumps in the equation. So once again, from -10 to 80 degrees outdoor air temperature along the bottom, from 0 to 65,000 BTUs up the left. On a -10 degree day, this guy needs 65,000 BTUs. On a 67 degree day, he needs nothing. If I were to put in a 3 ton heat pump, it'd be this baby blue line, 3 ton standard heat pump, and that, we'll call it 36 degrees outside. When I got below that, I couldn't generate enough heat with the heat pump. So everything in this triangle here on the left, I wouldn't be able to handle. If I put in the 3 ton variable speed heat pump, it then becomes this red line here. So that red line, as you can see, is a little bit flatter, not quite as steep as the baby blue line, because I'm able to control the compressor and condenser fan speeds in order to continue to maintain the BTUs that I want. So now I can get down to about 30 degrees outside air temperature, which is a bit of an improvement. And if you look back a couple charts, between 30 and 35, we're talking about an extra 600-700 run hours that I might be able to get if I did that, just by going to the 3 ton variable speed. However, if I upsize it, or if I heating size it, more for the 4 ton heat pump, it becomes this dark blue line. If I follow that guy along, when I get over to, we'll call it 16, 17 degrees outside, that's when I can no longer make enough heat. So that's a pretty big difference between 35 and 17. That's a couple thousand hours of runtime. So that's kind of where the advantage of this guy is going to fall into play, is being able to upsize him. There is actually an iPhone app as well as a website that Bryant and Carrier have that you can use to graph out that scenario for your specific customer situation. So I graphed one here randomly, a 4 ton heat pump on a 3 ton cooling load. So I graphed a 3 ton heat pump versus a 4 ton heat pump, a 3 ton regular heat pump versus a 4 ton green speed heat pump. And you can see that the blue line was the regular one, the green line was the green speed heat pump. All the operating hours in that green shaded box are hours that I now get to run my heat pump that I could not have done it with a regular system. So that's kind of the tool you can use. You can do it on your iPhone, download the app from HVAC Partners, or on HVAC Partners is also a website version you can use if you don't have an iPhone or an iPad. If you need help with that, talk to me later and I'll help you find where to download that from. This is the sizing chart right out of the book for these 2 extreme and green speed heat pumps. And basically they're trying to get you to round up. So if you had a 2 ton cooling load, they're saying put in the 3 ton heat pump, 36,000 BTU heat pump. You know, if you had a 3-ton, they're saying put a 4-ton in. If you had a 3.5, they're saying put a 5-ton in. And if you had a 4 or 5-ton cooling load, they're also saying put a 5-ton in. So you're not really upsizing on the 5-ton only because the biggest size they have available is a 5-ton. So you can't really get any bigger than that. But it'd be nice if you could, obviously, if they had a 6-ton. So you can see just based on this chart why we don't stock a 2-ton heat pump, because it would apply to a system that was only like a 1 or 1.5-ton cooling load, which is a pretty rare house these days. So this is kind of the sizing chart, and you'll see the big giant note on the bottom that basically says pay attention to the ductwork airflow. There's no point in giving someone a 4-ton heat pump on their 3-ton ductwork system if they can't move that air. So you got to make sure you can actually upsize it in a retrofit scenario. Let me jump over real quick and see if we had any new questions pop up. And we do not yet. So if you have questions, type them in the bottom right-hand corner of the screen, and I'll do my best to address them as we go here. All right, so HSPF, heating seasonal performance factors, how air source heat pumps are rated in the 1 through 5-ton residential size category range. Even if it's a commercial job, it's still a residential heat pump you'd be putting on it. Normally, traditionally, we've always talked about heat pumps in terms of SEER, just because we're used to that from the air conditioning world. However, SEER is incorrect term. SEER has never applied to heat pumps ever. Well, I shouldn't say that. There's a SEER rating for every heat pump, but it only applies for the cooling function of the heat pump. It has absolutely nothing to do with heating whatsoever. Every air source heat pump has a SEER rating and an HSPF rating. Both of these are AHRI published data. HSPF is the heating side, SEER is the cooling side. When we're talking about heat pumps and their efficiency, we really need to focus more on the HSPF, the heating season, versus the cooling season. I showed you earlier there's very few run hours for cooling relative to heating. All the energy savings for these type of heat pump systems is going to come off the heating season. Cooling time is not going to really give me a whole bunch of energy savings, just like it doesn't give me a whole bunch on a regular air conditioner. However, it's going to be fantastic for comfort and dehumidification, which is why you want to talk to people about these heat pumps in the summertime. But the money payback is going to come off the heating season. So HSPF stands for Heating Seasonal Performance Factor. SEER, as you probably know, stands for Seasonal Energy Efficiency Ratio. They both have something in common, which is the seasonal part in their name. That means these units are rated for different operating points for different temperatures. So they take into account several different things other than just the straight efficiency. They take into account the cycling of the units, right? So as these units cycle on and off, does that affect their efficiency? In terms of heat pumps, it also takes into account the defrost cycle, right? If my outdoor unit now becomes my evaporator coil, right? My indoor unit's my condenser. Well, if my evaporator's outside, that's where the condensation is going to occur in terms of air on the coil. And if it's freezing outside below 32, that condensation could freeze or frost the coil, so we needed to defrost it. The way we defrost the heat pump is by running it as an air conditioner again temporarily. So for whatever, 3 minutes or so, we're running air conditioning mode and basically use the heat from inside your house to thaw out the outdoor coil, and then we'll switch back to heating mode. Well, that solves our defrost problem. It does have a little bit of an energy penalty. So the HSPF number takes that into account and takes that penalty in there. So that's already represented. Additionally, when it gets really cold outside, the heat pump may not be able to keep up, and we need to turn on supplementary heaters such as auxiliary heat, electric heat. So that is also taken into account in this HSPF number. So those are both built in there. So heat pumps, air source heat pumps, as well as water source heat pumps are rated at 47 degree temperature. And the reason they are rated at 47 degrees is because the heating content of the air at 47 degrees is very similar to the cooling needs at 95 degrees, right? So we already test condensing units at 95, so then we retest these heat pump versions at 47 to see what their capacity happens to be. It's a really nice test because it's basically the same, deviation from set point compared to outdoor temperature as a cooling season. So 47 is basically 95. However, in terms of operation, people want to know what's going to happen when it's colder out too. So heat pumps get a second rating point at 17 degrees outside air. There's a 47 degree rating point and a 17 degree rating point for a heat pump, whereas an air conditioner would just have 95 degrees. So here's an example of a heat pump. This is not even the heat pump we're talking about today with variable speed. This is just a regular heat pump, a regular 7.8 HSPF legal minimum heat pump. Now remember, the heat pump we're talking about today is 1213H SPF. But even this regular one has a COP on a 47-degree day of 3.52, on a 17-degree day 2.46. So what's a COP, right? COP is coefficient of performance. We're comparing one heat pump to the other. We don't really look at this. We just look at the HSPF number, which kind of takes everything into account. However, it may be advantageous to look at COP when you're trying to compare an air source heat pump to a geothermal heat pump, because those products are not rated with HSPF. They are only rated with COP. Fortunately, the air source guys publish both, so you can make a comparison to geo if you want to, and we'll talk about that in a minute. COP, coefficient of performance, is just a ratio of how much power did I buy versus how much capacity did I get. So if I have a COP of 1.0, that basically means for every kilowatt hour I buy from the power company, I get 1 kilowatt of electricity, right? Or 1 kilowatt hour of heating capacity. So it's a 1-to-1 relationship. So a 1.0 COP means it's 100% efficient, right? So if I had the best furnace money could buy, which I believe these days is a 98% efficient furnace, the COP would be 0.98, right? So electric heat is 1.0, furnaces are 0.8 to 0.98, heat pumps are 2 to 4 COP, depending on the outdoor air temperature. But even at the 2 number, right, 2.46 on the right-hand side at 17 degrees over here, that's still 250% compared to 98% efficient on a furnace. So it's 2.5 times more efficient than the absolute best furnace you can buy. Every single heat pump, even the worst heat pump ever made, is more efficient than the best furnace or boiler ever made. Now, it doesn't mean it's the cheapest thing to run, right, because gas is pretty cheap around here, but it is the most efficient thing to run. We got to look at some other factors to see which one's less expensive to run in terms of money. If you want to compare to a geo system, you can do that. We got to use the COP numbers instead of the HSPF numbers. The other thing that comes into play is that the air source guys account for auxiliary heat in their efficiency numbers. The geothermal guys don't, so it's not really fair. It's not really apples to apples, but we can still go ahead and try to use it as a comparison. These are 5 different residential-oriented energy software tools that we use at our office here to compare things. Some of us use different ones for different reasons. The energy auditor is done by a company called Energy Design Systems. Some of you guys know it as Gizmo or Sprocket. That energy auditing tool can do air source heat pump comparisons and compare them to gas furnaces and show someone how much money they might save. It does not do geo though, but it will compare heat pumps to heat pumps and heat pumps to furnaces. GeoDesigner is the geothermal software that we use, and that does compare geothermal to other systems. It's slightly biased to geo, but overall it's a pretty fair comparison. Energy Audit is one of the ones I run on my machine. It's made by a company called Elite, which some of you guys probably use for load calcs. They have an energy auditing module you can add on to that. And that one's really nice because I can put in the efficiency points for various outdoor air temperatures to get an even better representation. The RightSoft guys have a tool called Comfort Builder. I know some of you guys use that. It has the ability to do heat pumps, and they also have iPhone and iPad apps for that. And then the one I'm going to use right now is called Online Op Cost Calculator. It's a tool specifically for Bryant and Carrier. You'll find it on HVAC Partners. It is also made by the RightSoft guys, but it's free and it takes 5 minutes. That's why I use this one quite frequently. So I'll show you that one here first. So the way this works, if you haven't used it before, it's really easy. Like I said, it's 5 minutes. I did some screenshots here of natural gas, propane, and electric customers, so you can see all 3 of the outputs. So you put your heating and cooling loads in on the left-hand side. Now these are the loads you put in, not the size of the existing furnace. So if somebody has a 100,000 BTU furnace, you don't put 100,000 here. If it's a 100,000 BTU furnace at 80%, you'd put 80,000 here. And then hopefully at some point you actually do a load calculation and find out what the real load is and then put that in here. Right? But so this is the heating load and the cooling load. You put the zip code so you can get the weather data. You say if you got natural gas or propane. In this case I picked natural gas. At the time I did this screenshot a year ago, I put in $1 a therm. If I were to redo it right now, I'd probably put in 75 cents a therm. I know you've probably all seen news articles about gas being down to 22 cents a therm. That's the raw cost of the gas itself. You also have to add in the distribution charges, taxes, fees, energy efficiency programs, and all that stuff. When I did mine for all my 2011 gas bills, I averaged 78 cents a therm throughout the year. Since then, it's gone down even a little bit more than that. So if I did it today, I'd put in 75 cents a therm. However, I did it a year ago, so I had a buck a therm in here. And then you put in your electric costs, and if they're different for summer and winter. I put in 10 cents at the time. If I were to do it over again, I probably would put in 12 cents based on last year's bills at my house. So once you put in those utility rates, your loads, and your zip code, then you can build 4 different systems here. One of them is the base system. You can put in the system the homeowner currently has today. That's what you would normally do. If you were doing new construction, like I did in this example, I put in a legal minimum system, which is 13 SEER and 80% efficient. But if you had an older system, you might put in 8 SEER and maybe a 70% efficient furnace because their 80%er 20 years later probably is no longer 80%. In any case, this is a legal minimum one for a gas furnace system. It's going to cost me $250 to run the cooling, $1,900 to run the heating based on this zip code and size. Overall, it's costing me $2,200. The second system, investment number 1 that I picked here, so what am I going to compare this to, right? I put in a 97% gas furnace with a 18 SEER air conditioner, so basically the most efficient thing I could find in the database here, and that's going to save me $600 a year over the legal minimum system. Not the system they have today, but over a legal minimum. Investment number 2 was a hybrid heating system with a 2-stage heat pump. So this was a 97% gas furnace with a 2-stage, actually this is a 1-stage heat pump. Entry level, 13 SEER. That guy's going to save me $670. Not very much savings over a top-of-the-line air conditioner, right? Investment number 3 was a variable speed, in this case, Carrier Green Speed heat pump bolted to a 97% efficient gas furnace. And overall, this guy was going to save me $850 over a legal minimum system. Or you can think of it as $200 over investment number 1, which is my normal top-of-the-line system. So the energy savings, as you can see, is not huge compared to a top-of-the-line system, but compared to somebody's older system, it might be a pretty good deal, maybe $1,100 or $1,200. But natural gas is pretty cheap, so it's pretty hard to get a payback that way. I'll show you propane in a minute, and the story's totally different there. But natural gas, you're not going to sell this heat pump to somebody based on natural gas savings. You're going to sell it to them based on comfort, and energy is going to come along for the ride. Other 2 things to note on this software, there's this little checkbox that says select for heating. It only pops up if you put a heat pump in here, and it's only allowed to be checked if you put in a variable speed heat pump. What that does is tries to upsize the heat pump one size. So I had a 32,000 BTU cooling load, so you would have thought that I would have put in a 2.5 or 3-ton unit. I guess a 3-ton because I don't have a 2.5 on the variable speed. But this guy put in a 4-ton heat pump in this software. He basically upsized him for the heating mode to get more hours. The other thing you'll notice is that the software gives you the thermal and economic breakpoints. It calculates that for us, so we don't have to do it on the chart. So that first heat pump, the entry-level one, says the thermal breakpoint is 41 degrees. That means when it gets below 41 degrees outside, that heat pump will not be able to generate enough heat to heat the space. Economically, it's saying the changeover point is 31 degrees. So when it gets below 31 degrees, at these gas and electric costs, it'll become cheaper to run the gas furnace instead of the electric heat pump. Then the variable speed unit, his thermal breakpoint was 17 degrees. So instead of 41, he can run down to 17 degrees outside and still get the full BTUs. And then electric gas cost-wise, when I get down to 23 degrees outside, it would be cheaper to turn the gas furnace on. So you can see that this variable speed heat pump is definitely going to be the most efficient choice I have. However, he's not hugely more efficient that he's going to save me so much money versus gas. I shouldn't say that. He's way more efficient. He's not hugely cost-effective compared to gas. However, if I have someone who has a propane system, which is this screen I just switched to now, the story is completely different there. You could definitely sell the heat pump based on gas savings alone, and then comfort comes along for the ride, right? So natural gas, it's a comfort story with an energy bonus. For propane, it's an energy story with a comfort bonus. In this case, I put in $2.30 for propane, which was the cost at the time. After the mild winter we had, it went down to probably about $2 a gallon, but it's still really, really expensive. And this guy, the thermal and economic breakpoints are, well, the thermal breakpoints are the same because they're the same furnace and heat pump. The economic breakpoint's different. So thermally, I can get down to 17 degrees just like the gas system. Economically, it's minus 18, whereas the gas one you saw was 23 degrees. Well, now it's saying run your heat pump down to minus 18, then put on your propane furnace. Now in the real world, I can't do that. I got to switch at positive 18 because I need to be able to get the thermal capacity and the economic benefit. But it's basically showing you here that propane is so overpriced compared to electricity that it always makes sense to run the heat pump. In this case, this guy's going to save $3,000 over a legal minimum brand new system, which would have cost him $4,500 to run. This system is only going to cost him $1,500 to run. So it's a huge payback on heat pumps for propane customers. And if you compare it against electric heat, there's also a pretty good payback story. In this case, the gas prices over here on the left don't matter because we're not using gas. Only electric matters. And you can see here, once again, the thermal breakpoints are basically the same, but economically it's saying run this heat pump down to minus 23 degrees outside. Basically never shut it off. Now in reality, I'm going to have to turn on electric heat to help him out, and that's accounted for in the software. But he's going to save $2,600 over a base system. So it would have cost $4,000 to run. Now it's going to cost $1,300 to run. So it's a pretty good deal. So if somebody is on propane or electric, putting in one of these variable speed heat pumps is practically a no-brainer. If they're on natural gas, then you got a decision to make. You got to do a little bit of math with them, and they might want it for the comfort benefits, which we're going to talk about in a second, but economically, it's probably a wash. Let me check the question box real quick before we move on. There was a quick question about the select for heating box that I mentioned on here. So on this software, you see on the two heat pump choices, it shows a little white box there that says select for heating. So it's over on the right side. I don't know if you guys can see my mouse or not. But I can't check it on the regular heat pump because I'm not allowed to upsize him because he won't run correctly in the summertime. On the variable speed heat pump, I can check it because in the summertime he can ramp down, in the wintertime he can ramp up. And what that does is tries to upsize my heat pump closer to my heating load. So instead of a 32,000 BTU cooling load, which would have gave me a 3-ton heat pump or 2.5-ton heat pump, this guy put in a 4-ton heat pump, 25 VNA 048. So that's why he's able to get down to those lower outdoor air temperatures. So hopefully that answered the question. If not, Jim, I think you asked the question. Just contact me afterwards and I'll clarify it even further if we need to. All right, a couple other things on this guy. A couple reasons why this guy is so much more efficient. One is that the condenser coil is much larger than it used to be. I shouldn't call it a condenser coil, right? I should call it an outdoor coil. Two things. Instead of having the coil on 3 sides like a traditional unit has and having the 4th side as an access panel, this guy actually has coil surface area on all 4 sides, and the corner of the unit is actually the access, as well as accessing it through the top through the condenser fan section. So from the service standpoint, that's less than ideal, but from an efficiency standpoint, it gave us a huge amount of surface area, which allows us to be much more efficient. Additionally, the coil is double rowed. So I don't know if you can see that on the drawing on the top left, but there's 2 rows of coil side by side. Somebody had asked me a couple weeks back if that's something you split to clean it in between, and it's actually not. It's 2 rows of coil sharing fins, so it's still like one giant coil, if you will. It's just double thick. So you cannot split it like I thought you could previously, but just mentioning that in case you happen to be on the call again. The variable speed capacity is what kind of makes this all work. So a normal unit, it's either running at 100% or 0%, right? A normal condensing unit or heat pump, it's either on or it's off. If I were to buy a 2-stage air conditioner or heat pump, in your mind, it'd probably go 0, 50, and 100% capacity, just when you kind of think about it. Oh, if I only run 1 stage, it's probably 50%. That's not really the way it works. It's really 0, 80, and 100%. When I shut off 2nd stage and I run 1 stage by itself, for most of these units, it's between 70 and 80% capacity, not the 50% that you probably imagined it to be, or that I imagined it to be anyway. So you're only stage down that much. Yes, it helps out having 2-stage equipment. It's way better than 1-stage equipment, but it doesn't ramp down all that much. These variable speed heat pumps, they can ramp down from 100 down to 40%. I forget exactly which ones. It's the 3 and 5 ton size, I believe, that goes down to 40, and the 2 and 4 ton size go down to 50. But they can ramp down, as far as 40%, and they operate in 1% increments. So a 3-ton heat pump would go from 40 to 100% in 1% increments. So 40, 41, 42, 53, 79, whatever. It's basically a 61-stage heat pump if you want to think of it in stages. From 40 to 100 in 1% increments is 61 stages. Plus 0, obviously. So we got much longer run time. If we can keep things running, it keeps the evaporator indoor coil wet, which keeps us dehumidifying longer. So this gives you an example here. The lowest capacity and highest capacity lines for a 4-ton heat pump. This black line represents the load of your house, right? Before we had it going the other direction because it was heating mode. Now we're in the cooling scenario. So now it starts down here with almost no BTUs at 65 degrees outside. And as it gets hotter outside, the line gets higher, which means we need more and more cooling capacity until we get up to, what are we at, 47,000 BTUs on a 95-degree day in this example. So normally I'd be shutting this thing on, off, 47,000 BTUs, 0. 47,000, 0. Giving you 55-degree cooling, 75-degree return air. 55 cooling, 75 return air. Clicking it on and off all day long. What the variable speed heat pump is going to do is try to keep this thing running continuously and never shut it off. By the way, it's going to do the same thing in the summertime, or excuse me, in the wintertime. It's going to try to run continuously and never shut off. That's his whole goal in life, is to constantly be running. However, running at much lower capacity, hence saving you tons of airflow energy. So as it gets cooler outside, he'll ramp down instead of cycling off. And as it gets warmer outside, he'll ramp back up the line. He's going to try to take this green line and match his capacity to match what your house needs at that moment. Now, at some point, it's going to get so mild outside, he's going to ramp down to minimum, for example, 40% on a 3-ton unit, that he can't ramp down any farther. And when we get to that point, the only thing he can do at that point is to actually shut off. So he ramps down to 40%, and it still gets milder and milder outside. He'll have to shut off. Then he'll cycle between 0 and 40% capacity, which is still better than going 0, 100% capacity, or 0, 80% capacity on a 2-stage unit. He'll go 0, 40, 0, 40. But when it's warmer outside, in this example, when it's above 77 degrees at this house, he's going to run nonstop all summer long and not cycle off until it gets below 77 degrees. The same thing happens in the heating mode. He's going to run, whenever it gets below, depending on the house, a certain temperature, 60 degrees or whatever, 50 degrees, and he's not going to shut off all winter long. There's only 3 times that this heat pump is going to shut off, whether it's summer or winter time. One is if you walk up to the thermostat and you change the set point. Let's say you asked for 72 degrees. Now you walk up to the set point in the summertime and you jack it from 72 up to 75. Well, this guy's going to ramp down to minimum capacity, 40%, and then he's going to say, wow, you want 75 and it's still 72 point something in here. I better go ahead and shut off for a little while. Right? So if you change the set point, he might shut off. If your time clock changes the set point, like for nighttime setback or daytime setback, he'll do the same thing, right? If you go to work and it automatically goes back to 80 degrees when you're not there, he'll end up cycling off for a while. The third time that he's going to cycle off is going to be if it's so mild outside he can't ramp down far enough. He'll have to actually shut off. That's only going to happen between probably 50 and 75 degree outdoor temperatures. Anything colder than that or hotter than that, he's going to be running. So there's a little bit of education you'll have to have with the consumer to explain to them that this heat pump is going to be running all the time. Because as soon as you tell them that, they're going to freak out and be like, what? It's going to run all the time? That's going to be a big energy waster. This guy's going to save energy over the course of the entire year, and he's going to run continuously, which is going to give them very good comfort, consistent discharge air temperature all the time. They're not going to get 55-degree air blowing in their face and then get 75, then 55, then 75. It'll be a consistent air temperature throughout the day. Same for heating mode. So it's going to definitely be a comfort story. And it's not going to cost them any more energy. They're going to be buying the same, actually they'll actually buy a little bit less electricity than they would have bought, or gas than they would have bought. And the reason they buy less is because once we reduce this guy's capacity, we're also going to reduce his airflow to match his capacity. So there'll be some extra savings there compared to a regular high-efficiency system. So the whole goal of matching this load is to get the longer run times. We want that. It's desirable because it gives us better dehumidification and more consistent, even temperature. It's actually easier on the equipment too, right? I also get that question on a lot of these classes is, well, if I run this compressor all the time, won't it die sooner? My answer always is probably not. It'll probably last longer. Generally speaking, things fail, mechanical things fail when they expand and contract, right? And they expand and contract because they're being heated up and cooled down, heated up and cooled down. Well, if I'm leaving this thing running consistently and I'm not turning it on and off, it's not heating up and cooling down, heating up and cooling down. It's staying the same temperature, right? So the compressor should last longer. The heat exchanger should last a little bit longer, or more specifically, the joints where the heat exchanger is attached. I think it's going to last longer. I don't have 20 years of data to prove that because we only had these things in the field for a year, but I'm guessing it'll probably last longer. And if we draw parallels to our commercial variable speed compression systems that we've been using, like on the Panasonic and Sanyo VRF systems that we've been doing for the past 3.5 years, we've had 0 compressor failures on one of these Sanyo EcoI VRF systems that we've been doing for 3 years. Not a single compressor has failed on a job in the Chicago area that we have done. I'm sure I just jinxed somebody's job site, but we bought 0 replacement compressors for these variable speed systems commercially. I imagine the same story is going to happen residentially. Things last longer when you modulate them than when you bang them on and off. This also gives you an idea on how much of a dehumidifier this guy can be. This is a 3-ton unit. On the left side, it's how much moisture is being removed. So that first blue bar there where it says standard 3-ton plus April Air 1750, saying it's removing 175 pints per day of moisture out of somebody's house by having both their 3-ton air conditioner and their whole house dehumidifier running at the same time. If I were to put on just one of these 3-ton Carrier Green Speed or Bryant Extreme heat pumps, I'm going to get, we'll call it 130 pints per day. I'm going to get almost as much moisture removal as this other system that has a special dehumidifier added. But look at on the right side, on the energy side of the equation. I'm going to do it with like 1/3 of the power, right? So I'm going to be able to get almost as much dehumidification, and I'm not going to waste any energy doing it. All that is because this guy stays running continuously at a low capacity. That's where that dehumidification power is coming from. Sound-wise, this guy is going to be a fairly quiet unit as well. And some of that's because of the sound technology put into the unit. A lot of it's because we're going to ramp him down. Both the compressor and condenser fan are going to be ramped down on low load scenarios. And most of the year, we're going to be at some kind of low part load scenario. So most of the year, we'll be running less than full RPM. So we'll be quiet most of the time. And this gives you an idea of the sound level differences if you want to look at that. dBA is probably not a very meaningful concept to an end user, but I want to say you have to probably go down about 3 dBA for someone to even be able to audibly notice a difference. And if you go down, I want to say, what's the rule, like 6 dBA, it's like cutting it in half, right, the sound in half. So it can be a substantial difference if I'm able to ramp this guy down. Some of the things that are in this unit that make it so quiet is it has an internal muffler system on it. It also has an external muffler that ships with it. You can see that up in the top right there on the little brick wall that muffles some of that sound. It's kind of like a silencer on the barrel of a gun. The fan blades are shaped in such a way that they reduce sound. We do this on some of the other Bryant and Carrier high-end condensing units anyway, so that's already built in. But it's what we call a forward swept blade. And I'm told that the guys at the Sikorsky Helicopter Group helped the Carrier guys design this. So I don't know if that's impressive to you or not, but apparently they know about airflow. This guy has 2 sound compressor blankets on him, right? So there's a square one on top, and then there's a traditional round one on top of him underneath that. It has vibration isolators. So if you can see in the bottom right, it has all these grommets here that it's posted on. So the 4 ends of the compressor are posted on a rubber grommet that isolates the sound, and that's mounted to a laminated plate instead of a regular sheet metal plate. So lots of things that go into this guy to make him a little bit quieter than the average unit. Plus, he runs at a different speed. Some of the pieces inside this unit that are a little bit different than a regular heat pump or condensing unit, there's an electronic expansion valve, which is kind of like a TXV, a thermal expansion valve, but instead of doing it thermally, we do it electronically, which means that the control system actually modulates the position of the expansion valve to what it wants to see. We still have a TXV on these kind of projects. There's a TXV over at the indoor coil for cooling mode like it normally would be. The EXV is inside the heat pump factory installed for the heating mode, and it's a 600-step EXV that we position to the right capacity. In the cooling mode, refrigerant's flowing backwards and it basically is full port open, and the heating mode we modulate it down. There's a charge compensator, which for lack of a better description, his job in life is to allow us to buffer some refrigerant in the container so we can account for the fact different refrigerant amounts are needed for both heating and cooling so we don't send any gas back to the compressor. It's got an inverter, which is the key to this whole thing. An inverter is basically a VFD. It's a variable frequency drive. We use that to change the frequency of the power coming into the compressor and hence modulate its capacity. The compressor itself is variable speed, ready to accept a signal from that inverter. The compressor is actually a DC compressor, right? Whereas most compressors we use are AC, alternating current. This is DC, and the reason for that is an inverter, like a VFD, every time you convert power from AC to DC and back again, it wastes some energy, which is basically heat, right? Put your hand on a VFD cabinet, it's always hot. It's wasting energy that way. If we have a DC compressor, it's one less conversion point, so one less waste of energy, if you will. Some of these components inside the unit, if you took the coil off them and looked in there, there's the EXV. I'll show you a picture of that in a minute. That's a 600-step EXV used to position refrigerant flow going into the unit. There's that charge compensator. Well, actually, that might be the external muffler. The charge compensator is probably the green one in the back. I think the wrong box is circled there. Probably that big green one is the charge compensator, and the blue one is the external muffler. Variable DC compressor. There's some extra sensors on here. There's a suction line pressure transducer. There's also a suction temperature thermistor that are feeding back into the controller. There's the expansion valve, 600 steps. He's that little black guy right there. It's like the top of a beer can kind of thing. That's the inverter, the VFD. So you can see electronics on the side of this unit. That's the access section as well. If you took this whole section off, you would be able to get into some of the components like the expansion valve and the reversing valve. The inverter is the top half guy there with the black cover on him. And down in the bottom you see a picture of what it looks like on the back side with all those fins. That's to dissipate heat away from the inverter to keep it cool. There's what it looks like from the top view with all the components on the inside. So the black unit obviously in the middle is the compressor. Normally he would have 2 sound blankets on top of him. That blue guy is the muffler. The black guy on the right side is the charge compensator. Down in the middle, the brass colored one is the reversing valve. So that guy switches it between heating and cooling mode. And over on the far right side, if you can see it, the little black top is the electronic expansion valve. So there's quite a few components in this guy. The compressor itself is a Copeland compressor. Like I said, it's a DC compressor. It's variable speed. It is exclusive to Bryant and Carrier, right? So they're the only ones that have access to this compressor. I imagine down the road they'll probably open it up to other manufacturers, but right now Bryant and Carrier worked to help develop it, so they got an exclusivity deal on it. I know that one of our chiller manufacturers that we deal with at TEC is looking to have a unit come out, a 5-ton chiller, using this exact same compressor this summer. But as far as air conditioners go, Bryant and Carrier appear to have a pretty good exclusive deal on it. You can do low ambient control with these guys, down to 0 degrees without adding anything additional. Because the condenser fan is already variable speed, we don't have to add anything special there. The Infinity and Evolution controls can already ramp him down for low ambient usage. And there's also an internal heater, sump heater, so I don't need to add a crankcase heater on there. You probably still need to add wind baffles if you're going to put this on a roof or something like that where you're going to have direct prevailing wind. All right, the last thing we're going to talk about a little bit here is the airflow scenario. Let me just check real quick if there was any additional questions that popped up. And there's none right now. If anybody has any questions, go ahead and type them in the box in the bottom right, and I'll answer them here at the end. This just shows you what happens on a normal 2-stage heat pump or air conditioner. So in this example, I'm running 1050 CFM for this 3-ton heat pump. When I run only one stage, I reduce the airflow down to about 140 CFM. Right, because I'm not really cutting the compressor speed in half. I'm only cutting him down from 100% down to like 80%. So I only can do the same thing with the airflow on the indoor unit. We'll look at one of these variable speed Bryant Extreme or Carrier Green Speed heat pumps. It's a much different story. I'm able to ramp this guy down much further on the compressor side, so therefore I can ramp him down much further on the indoor unit's airflow side. So in this case, for a 3-ton unit, I'm able to reduce him down about 60%. So instead of cutting his airflow back 20%, I can reduce it 60%. That ends up saving me a couple $100 extra a year on fan energy. In addition, it allows me to work very well with zoning systems, which we'll talk about in a second here. So here's what would happen on a zoning system. Not only can I cut down the airflow back more because I have the variable speed compressor, I'm also allowed to cut it back even a little further with the zoning system. So instead of a 60% reduction, I can get even down to like a 70% reduction in airflow. In this example, going from like 1100 CFM down to 350 CFM on a normal type cooling day. This guy is very, very adaptable to zoning systems. It would be the preferred type of condensing unit / heat pump that you would put on a zoning system. None of our other units would be able to operate on this low of an airflow condition. How often can you take a 3-ton unit down to 300 CFM? You're basically running like a 1-ton unit when you got one of the smaller zones calling for cooling by himself, or heating for that matter. So this guy is definitely the quote-unquote zoning unit. Then here's a 4-stage example, right? Similar kind of scenario. Not quite as dramatic as the 3-stage unit, but still, normally I'd only be able to cut back the speed about 15%. Now I'm going to be able to cut it back about 40% with the variable speed unit. If I put the variable speed unit on a zoning system, I can cut them back about 60%. Now, with that being said, these condensing units / heat pumps have to be combined with those Infinity and Evolution furnaces and fan coils, and they have to be operated by one of the Evolution or Infinity wall controllers. You cannot use them with a regular thermostat. They have to be used with the Evolution and Infinity controls, because that's the guy that's going to take responsibility for coordinating the blower speed with the condenser fan speed, with the compressor speed, with the EXV position. All those things got to be coordinated together, and you have to have that controller on the wall to do it. Now, with that being said, there's a little jumper you can cut and put a regular stat on there to run him in temporary emergency mode, like over a weekend or something, while you wait to get a new stat if you knocked it off the wall or whatever. But generally, for regular operation, it has to be used with those controls in order to ramp up and down. With that being said, if you put it on a zoning system, he has to be used with an Infinity or Evolution zoning system. If you're familiar with those zoning systems, you already know those systems do not have bypass dampers. You cannot use them with a bypass damper. They have to be allowed to ramp down on their own, and the fan system controls the capacity instead of a bypass damper. So as zones start shutting down and airflow gets restricted, duct pressure builds up, we have to have the ability of the fan to actually slow down. And that works on these zoning systems with the heat pumps even better than with a regular one. All right, with that being said, let me look and see if we had any more questions come up. I got a question from Greg on what controls compressor speed. So I'm not sure if you mean what physically controls it or what conditions control it. But what physically controls it is the Infinity or Evolution circuit board inside the furnace, and he's getting his data from the controller on the wall. So that controller on the wall is feeding data into the furnace circuit board, and he's not like a regular thermostat. He doesn't say, I want heating or I want cooling or I want 1-stage or 2-stage heating or whatever. What he does is he sends over his data. So he sends over what set point do I want, let's say in this example 72 degrees, and what temperature is it really here right now. Let's say it sends over that it's 73.5. So you're asking for 72, it's 73.5. He calculates that he's 1.5 degrees out of set point. So he'll turn on this unit and ramp him up to a middle speed, let's say, for sake of argument, and then he'll remonitor that, and every couple seconds he'll look at it and recalculate it again to see how fast or how slow he's getting to that set point. As it goes from 73.5 down to 72, it'll adjust how much capacity it's running so it arrives exactly at set point at the right time, and then it continues to run at that capacity that's needed. It's basically a PID loop. If you're familiar with commercial controls, it's a PID loop like we'd use on a hot water or chill water modulating valve. That's the kind of thing we're using on this controller. What's the set point? What's the desired set point? And what's the actual temperature? And how fast or how slow am I getting to that? So that's what's going to ramp this thing up and down. There is another note in here asking if there's a way to run the fan off of duct static. And the answer to that is yes and no. It's already going to be running on duct static pressure. So it's already going to be, as zone dampers close, duct static pressure builds up and we will slow the fan down. However, it's not doing it with a duct static pressure sensor. What it's actually doing is it's getting feedback data from the ECM motor on the variable speed fan. It's getting feedback data from the motor on the variable speed fan, and it's using that to calculate what the duct static pressure is and ramp up and down accordingly. Because it's doing it that way, it also can calculate when filters are dirty and alarm on the screen if the filter pressure changes over time. So it can do those kind of things as well. Is there any additional questions that anyone has? Okay, if there's no additional questions, then I'm going to go ahead and stop the webinar. If you have any questions, please do give me a call. My phone number and email are on the screen there. Thank you.